Hi there. So, welcome to assignment 36. This is solving day 3. Okay, and let's start with some bell work. Solve 0 to 2 pi cosine squared 3 theta equals cosine 3 theta. All right, so give that one a try. Okay, welcome back. So what I don't want to see, I don't want to see you dividing both sides by cosine 3 theta. Don't do that. Please, please don't do that. Instead, I really want you moving this over. When you divide by a trig function, there's a good chance you're throwing solutions away. So try not to do that. Here we could make this as cosine squared 3 theta minus cosine 3 theta equals 0. Well, now that my binomial, quadratic binomial, is equal to 0, I can factor. I'll factor out a cosine 3 theta. I'll get cosine 3 theta minus cosine 3 theta divided by cosine 3 theta is 1. And so, yeah, I'm getting cosine 3 theta equals 0, just like if I had divided. I'm sorry, let me start that again. I'm getting cosine 3 theta equal to 1 here. And that's what I would get if I divided both sides by cosine 3 theta. These would turn into 1. And over here, this would cancel one of those. And so I have cosine 3 theta equals 1. However, cosine 3 theta also equals 0. And so if you divide both sides by cosine 3 theta here, you're going to throw away all these solutions. Yeah, that's not cool. So don't do that. Try not to multiply or divide by a trig function. And in fact, you might want to say, hey, if I end up having to divide or multiply by a trig function, then it's a must-check situation. And I recommend must-checking it that way. Look on the calculator. Because it's not that your answers won't work, it's that you won't have enough answers. Yeah? So if I have cosine 3x close, if I have cosine 3x squared, cosine 3x squared, and then I put here, some more stuff there. Okay, and here I put cosine 3x. And I am looking on 0 to 2 pi. So I've got 0 to 2 pi, and go. So that's the cosine squared with all its bounciness. And here's the cosine 3 theta. And, wow, they appear to be intersecting, are they? Let me change my viewing window a little bit. They're not actually touching there. But look, I see some points of intersection. And if I turn this into cosine 3 theta equals 1, that's the guy who divided by cosine at the beginning. I see instead, oh wait, so that's cosine equals 1. I don't want this one to show up. Okay. I get 1, 2, 3, 4 solutions this way. But I know that there's more because I saw already that there would be not just 4 solutions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I see a lot of solutions here. Well, I guess I'm not including that one. Right? And so I'm saying must check, but not must check to take my answers and plug them in, but instead must check to graph. So what do we have here? We have cosine squared 3 theta equals cosine 3 theta. And I said, hey, let's subtract and not divide by cosine 3 theta because that's going to bring too few answers. So now we've got cosine squared 3 theta minus cosine 3 theta equals 0. And we're going to factor out a cosine 3 theta. And we're going to be left with cosine 3 theta minus 1 equals 0. Watch out for this. Cosine 3 theta divided by cosine 3 theta is not 0. It's 1. I've got this minus 1 here. So I end up with cosine 3 theta equals 0. And cosine 3 theta equals 1. Okay, if we're doing 0 to 2 pi, when does cosine equal 0? Well, that happens at pi over 2, pi over 2, pi over 2, 7 pi over 2, 1 pi over 2, and 11 pi over 2. Remember, this is on 0 to 2 pi, so I have to go around that many times picking up solutions, and then divide those solutions by that b value. Pi over 6, pi over 6, pi over 6, 7 pi over 6, 9 pi over 6, 11 pi over 6. 12 pi over 6 would be 2 pi. And this is just less than that. Okay, and that's when cosine is equal to 0. What about cosine equal to 1? Well, that happens only at 0, 2 pi, and 4 pi. If I divide everywhere by 3, do you want to include 5 pi? And 6 pi? Because we were supposed to go around 3 times. Plus, what is this? I think that's it, but let's check. 3, then let's do theta. I'll divide all of those by 3. And that doesn't work because that is 2 pi. And I do have these solutions. And I can, of course, always check these solutions. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, that's certainly the 10 solutions that I counted originally. Okay, so please, don't make up algebra here. Don't divide by a trig function or multiply by a trig function if you can avoid it. And if you do end up doing that, please must check with your calculator. Wow, that was a good question. Okay, how about this one? Solve. Problem says solve. That's the directions. Cosine squared 3 theta equals cosine 3 theta. Solve. Okay, so, yeah, this is the all solutions one. So show me how to do this one with all solutions. Pause the video, give it a try. No, you really need to be practicing. I promise. If you practice this now, you're more likely to be able to do it on your assessment. Hey everyone. So, did you end up with cosine squared 3 theta minus cosine 3 theta, and then you factored cosine theta out, and left with cosine 3 theta, minus 1 equals 0. Okay, so we know cosine 3 theta equals 0. And so because we're doing all solutions, I'm only going around once. When is cosine equal to 0? Cosine is equal to 0 at pi over 2 and 3 pi over 2. Here, I've got cosine 3 theta equals 1. I'm only going around once, so I've got 3 theta equals 0. Kind of think I need the 2 pi, but I'm not sure. So let's take a look. Here, we're going to, before we divide, we're going to slap on those plus 2 pi ends. Oh, and so this will include that one. Okay. And then divide everywhere by 3. So I should end up with theta equals pi over 6 plus 2 pi n over 3. And 3 pi over 6 plus 2 pi n over 3. And here, 0 plus 2 pi n over 3. And of course, you could leave that 0 off. All right? Oh, wow. That's some good thinking here today. Okay. And this is the last of my Bell questions. It's cosine theta equals negative 1/4. Can you solve that one? Yeah, let's do all the solutions. Okay. How'd it go? What'd you do? I don't know when cosine is equal to negative 1/4. I agree, I don't either. I know that cosine is the x values, and the x values, if this is negative 1, negative 1/4 will be over here. And if I'm thinking about my unit circle values, I'm looking at this angle here, but I don't know what that angle is. I know that negative 1/2 is 2 pi over 3. So this is between pi over 2 and 2 pi over 3. That's all I know about this. That's why this problem is only done these days with calculator. So if I graph cosine in y1 and I graph negative 1/4 in y2, and I'm looking 0 to 2 pi, I graph how many solutions? Well, we expect to see 2. There's 1, and there's a second one. So second quadrant, third quadrant, I get some solutions. Okay, so where are those solutions? Second, calculate intersect. Bring my cursor close to the point of intersection. Enter, enter, enter. And I get that theta equals 1.8237. Okay. And there was a second solution. Second, calculate intersect. Bring your cursor close to that point of intersection. And enter, enter, enter. And so I get theta equals 4.4597, so 460. Okay, and we wanted all solutions, so plus 2 pi n, plus 2 pi n. Okay, I can do this. I can do this the old school way, where I take the inverse cosine of each side. Cosine theta, 1/4, cosine inverse, and here I've got theta equals cosine inverse of negative 1/4. Okay, that's one solution. What's the other solution? So if I do inverse cosine of negative 1/4, I get this number. And that was that one. Great. If I add pi to that number, I get this, and that's not that. Right. So where's this other solution? Well, it turns out that the other solution is 2 pi minus cosine inverse of negative 1/4. So 2 pi minus inverse cosine negative 1/4. And look, there it is. Why? Because I'm using reference angles from section 4.4 in our textbook. Reference angles used to be really, really important so that we could use our reference angle formulas to help us find things like this. Except that this, yeah, this wouldn't be the right reference angle formula for third quadrant. Third quadrant reference angle formula is theta plus pi. And when I added pi to this, it didn't work, which is another reason why I don't think we should be using reference angles anymore. Just use the calculator. Okay? So, new school, old school. We're in new school. All right. So what do you want to do today? We've sort of gone through all the things. I thought we could just maybe just practice a little bit. So let's do some practice. Actually, this one, did you talk about this in class? Sine pi x plus cosine pi x will be on 0 over 2 pi. Okay, so this is not the, well, could it be? Because some students say they want to do this. They'll say negative cosine pi x equal to sine pi x. And they say, all right, when do the sine and cosine have opposite values? Sine and cosine have opposite values at pi over 4, no, at 3 pi over 4, and at 7 pi over 4. Okay, but I'm supposed to go around this many times. All right, so I'm going to have 11 pi over 4, and I'm going to have 15 pi over 4, and I'm going to have 4, 19 pi over 4, and 23 pi over 4. And divide everywhere by pi. So x equals 3/4, 7/4, 11/4, 15/4, 19/4, and 23/4. Well, the problem is that 0 to 2 pi is 6.28. Oh yeah, 24 over 4 would be 6. So those work. Wow. Yeah, could I do that? Sure can. Let's confirm that. So over here, we've got sine of pi x, don't forget to close that parentheses, plus cosine of pi x. And we're just looking for x-intercepts of this graph. Okay, so graph 1, 2, 3, 4, 5, 6 x-intercepts. And let's change the scale to be fourths. 0.25. Look at that. 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, these are the answers. But these are the answers. Now, what about doing it? Because, look, I want to say, if you're able to sort of conceptually wrap your head around when are the sine and cosine values opposite, those sine and cosine values are opposite at pi over 4 over 3 pi over 4, which has negative root 2 over 2, root 2 over 2, and 7 pi over 4, root 2 over 2, negative root 2 over 2. That's what this is saying. When are the sine and cosine values opposites of each other? Only at these places. If you can do that conceptually, wow, that's great. Most students can't do that. Instead, we're going to square both sides. And so sine squared pi x plus 2 sine pi x cosine pi x plus cosine squared pi x. Okay, and again, sine squared plus cosine squared equals 1. Okay, 1 plus 2 sine x, sine pi x cosine pi x equals 0. And so I'm going to subtract 1 and divide by 2. And so I'm now going to have negative 1/2 is this. Okay, so so sine pi x equals negative 1/2 and cosine pi x equals negative 1/2. So when does sine equal negative 1/2? Well, that happens at pi x equals 7 pi over 6 and x and 11 pi over 6. And now I've got a problem, because if I divide these by pi, I've got 7, 6, and 11, 6. I didn't see those answers before. We didn't know. We had 3/4 and 7/4. Oh, that didn't happen here. What? Why? I hear you saying. Yeah, so that's awkward. It's awkward. So these definitely not here. And even when I divide by pi, right, I'm getting those numbers versus those numbers. Well, maybe my answers happen over here. What about cosine equal to negative 1/2? Well, cosine's equal to negative 1/2 at 2 pi over 3 and 4 pi over 3. And if I divide by pi, I get 2/3 and I get 4/3. And again, these numbers aren't the numbers we got. Well, what's up here, Mr. Kipra? Well, so what's up here is it's a small, subtle disconnect. And the small, subtle disconnect is, if we have a 1 here, we could do this problem with no difficulty squaring both sides. But because we have a 0 here, and we get to this place where we have 0 equals 1 plus 2 sine pi x cosine pi x. Because we get to this place and then we think, oh, okay, I'm going to subtract 1 and divide by 2. Yeah, that's where our issue is coming. Yeah, this is not, I can't do that here. That's where I'm running into this problem. And no, I don't really have another way to solve this. In fact, what I would say to you is, why don't you just graph it? And yeah, graph it, or be that person who can see that negative cosine pi x equals sine pi x. No, you don't have to worry about anything that hard on our tests and quizzes, of course not. But if this were honors pre-cal, Trig, yeah, why not? That would be a scary nightmare, I think. Okay. So how about this? Why don't we practice with this one? Something a little more humane. Something that is test-worthy. 2 cosine squared x minus 5 cosine x plus 2 equals 0. And how about all solutions? Okay. Why don't you take a moment to solve that equation, find all solutions, and we'll check it over in a moment. Welcome back. Did you factor? So we got 2 cosine x, and cosine x, and 2, and 1, and some minuses. This gives me cosine x equals 1/2, and this gives me cosine x equals 2. It'd be really great if you looked at this and said, cosine can never equal 2. The highest cosine gets is 1. 2 is up here. When is cosine equal to 1/2? Cosine is equal to 1/2 at pi over 3 and at 5 pi over 3. Don't forget to add your plus 2 pi ends, because you have all solutions. Okay? All right. How about this one? Tangent squared x minus 6 tangent x plus 5 equals 0. Give that one a try. Hey, welcome back. Yeah, let's still talk about, oh, well, the last one was all solutions, so I'll do 0 to 2 pi here. Yes, this is factorable. Hey, and anytime it's not factorable and you say, oh, I could do it with quadratic formula, dude, if you're going to say quadratic formula, then you should just be graphing it and finding your solutions that way. So that's a -5 and a -1. Now, I chose this problem for a reason. And the reason I chose this problem is because most students say that this is not possible. It's not possible for tangent to be equal to 5. And here's what I want to say. I agree. If this said sine equal to 5 or cosine equal to 5, there's no way that they could be equal to 5. But this is tangent equal to 5. And one of the reasons that we did the graphing of our trig functions, including tangent, was so that we could say, here's the line y equals 5. Why, look, I've got 2 solutions. And really common on our next assessment is, no, kids are crossing this out. Stop it. I mean, you could go old school and say x equals inverse tangent of 5 and pi plus tangent inverse of 5. Those are those 2 solutions. Here, when is tangent equal to +1? Yeah, no problem. We know tangent is equal to 1 when sine and cosine have the same value. And so those are these angles. And I would like those angles. There's no reason for you to use a calculator on that. But here, yeah, we're not going old school. The way you're going to find this is you're going to graph tangent, and you're going to graph the line 5. Better change that viewing window so it goes up to 5. Let's say that. And graph. Okay, so second, calculate intersect. Bringing my cursor close to the point of intersection. And hitting enter, enter, enter. And I get 4.515. Oops, 4.515. Okay, now just to check, what if I said inverse tangent of 5 plus not bad. Same. Okay. And so if I take this and subtract 5, yep, that's my other answer. And let's confirm it on the graph. Second, calculate intersect. I'll bring my cursor close to that point of intersection. Enter. And there we go. Okay. So, yeah, 4 solutions. Please watch out for this. Please make a note for yourself about this. Tangent can be equal to a number bigger than 1 or a number smaller than -1. Okay. So, what do you want to do next? I don't know. I just got more of the same. So, part of me wants to say, look, if you feel comfortable with this, then move along. And I'll just do some other sample problems to practice with you. Yeah. Okay. Sine 2 theta equals 1. How about all solutions? Okay, when does sine equal 1? Well, that happens when theta, 2 theta equals pi over 2. And remember, it's all solutions, so I'm only going around once. I'm slapping on the plus 2 pi n, and then I'm dividing. by 2. So theta equals pi over 4 plus pi n. Good. Nice. That was it. If I wanted 0 to 2 pi solutions, well, that's when I have to go around the unit circle twice. So when does sine equal 1? Well, that happens at pi over 2, but I go around again. That also happens at 5 pi over 2. And then I divide everything by 2. And I get theta equals pi over 4 and 5 pi over 4. Okay? You know, if you went around once more, you would 5 pi over 2, I have 9 pi over 2, 9 pi over 4, and 9 pi over 4 is bigger than 2 pi. Yeah, so it's just these solutions. Okay, how about this one? Cosine 2 cosine 3x minus root 3 equals 0. Let's give that one a try. Yeah, I agree. Cosine 3x equal to root 3 over 2. Oh, and you were wondering what 0 to 2. Okay, so when does cosine equal root 3 over 2? Well, that happens a bunch of times, doesn't it? That happens at pi over 6, and it happens at 11 pi over 6, and if I add 2 pi to that, 13 pi over 6, and 23 pi over 6, that's the second time around. And again, I'm adding 2 pi, or 12 pi over 6, and I get 25 pi over 6, and if I add 12 pi to this, I get 35 pi over 6. So now I want to divide everywhere by 3, pi over 18, 11 pi over 18, 13 pi over 18, 22 pi over 18, 25 pi over 18, and 35 pi over 18. 36 pi over 18 is 2 pi, so I know all these solutions are within 0 to 2 pi. Good. Oh, did I say 0 to 2 pi? I meant just all solutions. Give me all solutions here. What would all solutions be? That's right. I'm only going to go around once. So I got pi over 6 plus 2 pi n, and 11 pi over 6 plus 2 pi n. Now if I divide everywhere by 3, not just here, but here as well. Not just here, but here as well. I end up with x equals pi over 18 plus 2 pi n over 3, and 11 pi over 18 plus 2 pi n over 3. Okie dokie. Okay. And what about this one? Sine x equals negative 0.8 on 0 to 2 pi. Will you find those solutions? Right. I've got to pull out my calculator for this. I mean, I know that sine is going to go and cross negative 0.8 twice. Once in third quadrant, once in fourth quadrant. I know that's third quadrant because this is pi. This is 3 pi over 2. And on my unit circle, from pi to 3 pi over 2, I'm in quadrant 3. And from 3 pi over 2 to 2 pi, I'm in fourth quadrant. And where is sine negative? Third and fourth quadrant. Okay, so lots of ways of knowing that my solutions were going to be 2, and they were going to be in third and fourth quadrant. But I have no idea where those, what angles have those heights, so I have to use my calculator. And again, I'm not going to do inverse sine. I mean, talk about a dilemma here. Let's find them graphically. Negative 0.8. And here we have sine x, 0 to 2 pi, y minimum negative 1 to y maximum of 1. Okay, great. Okay, and so I get these solutions. Second, calculate intersect. Bring close to point of intersection. Enter, enter, enter. And I get that this point is at 4.069. And what about that one? Second, calculate intersect. Enter, enter, enter. And I've got 5.356. Okay. Now let's try inverse sine. Inverse sine negative 0.8. Oops, I meant to be on the main screen. Inverse sine negative 0.8. That's negative 0.927. Hey, guess what? That's none of these answers, nor is it on 0 to 2 pi. So that's a problem. Remember, inverse sine goes from negative pi over 2 to pi over 2. Inverse sine will never find these for me. Yeah, I just found that one. Now, if I add 2 pi to that one, I can get this one, but not that one. So please, don't muck around with old school things. Just graph. Graph this on that interval by using your window, and that's x min and x max, and do second calculate intersect. You'll be so much happier you did. Okay? All right, how about this one? How about 6 cosine squared x equals 7 cosine x plus 2? Yep, and let's do it on 0 to 2 pi. Okay, give it a try, see what you come up with. And you know what I really want you to be thinking about when you look at a problem like this is 6x squared equals 7x plus 2. What would we do here? That's right. You see the quadratic and you move everything to one side so that this equation can be equal to 0. Like that. And now we factor. So we get 3 cosine x and 2 cosine x, and we get 2 and 1 and, oh, do we? Oh. I was going to say, minus, because then I would have minus 4, minus 3 for minus 7. But that's a problem. That's a problem. Well, can I now factor this? Well, let me think. Negative 12, that adds up to negative 7. Okay, I've got negative 1 and 12. And I've got negative 2 and 6. And then negative 3 and 4. We've got negative 4 and 3. Negative 6 and 2. And negative 12 and 1. Do any of these pairs add up to negative 7? No, none of them do. Does that mean it's not solvable? No. What we would have done with this equation, 6x squared minus 7x minus 2 equals 0, is we would have said quadratic formula. And here too, you can say quadratic formula. Except when you sing the song, instead of x equals negative b plus and minus square root, you have to say cosine x equals negative b. Yeah, cosine x equals. Wow, what would that even look like? Well, just out of pure curiosity, I'm going to say negative b plus and minus square root of b squared minus 4ac all over 2a. Okay, so I can do this. 24, 48. Oh, that's going to be 1. Huh. This looks like a factor. It's going to be 8 over 12. 8 over 12 is 2/3. And 6 over 12 is 1/2. Well, clearly I blew the factoring. So I think I feel like I need to go back and check that again. 0. Okay, so we've got 6 and 2 and cosine and cosine. No, I can't. All right, these are solutions. Cosine x equals these, which means 3 cosine x minus 2 was equal to 0, because I added 2 and divided by 3. And the other one was 2 cosine x minus 1 equal to 0. Okay? Minus 4. But that's plus 2 again. It's not a plus 2, it's a minus 2. So I think something went amiss with quadratic formula. I know, Google's going to go down another rabbit hole. Yes, I am. Cosine x equals negative b plus or minus square root b squared minus 4ac. Oh, I didn't do minus. All over 2a. Okay, so that is going to be 48 plus 49. And I get 97. Yep, that's why it's quadratic formula. Sure. But now, let's think about it. All right, I've got this with quadratic formula. And I'm going to do 7 plus root 97 over 12. But I can't do that by hand. I'm going to graph this, and this is 2 sets of solutions. And graph, yeah. So I think instead of going to that place, since when you use quadratic formula in these problems, it's gonna mean that you're gonna pull out your calculator anyway. Why don't you just graph this and find the x-intercepts? Or even graph this in y1 and this in y2 and do second calculate intersect. And if you want to see Mr. Paz do either of those approaches, by all means, you should ask him. I do get 2 answers, 1.81 and 4.473. For those of you who did pull out your calculator and check this one. All right. We've done those. I feel like we've done a whole bunch of those. Yeah, let's do that one that was quite similar to this one, actually. 6 cosine squared x equals 7 cosine x minus 2. That is the one that I've been inadvertently doing, because when I move everything to one side, 6 cosine squared x minus 7 cosine x plus 2 equals 0. Yes, that does factor nicely. 3 cosine x, 2 cosine x, 2 and 1, and a minus and a minus. And so I get cosine x equals 2/3, and cosine x equals 1/2. Well, we should know when cosine is equal to 1/2. That happens at pi over 3, 5 pi over 3. But when is cosine equal to 2/3? Yeah, no, sorry, going out the calculator. And I'm graphing cosine in y1, and I'm graphing 2/3 in y2. Graph. There's my cosine graph. There's my line y equals 2/3. And so I've got second, calculate, intersect. And bring that cursor closer to one of the points of intersection. And I get 0.841. And I go look for that other point of intersection. There we go. Scooch, scooch, scooch. I want to get close enough for my calculator to recognize this point instead of this one again. Okay, so I get, oh, and yes, that is the first curve. Second curve, yes, no. And we get 5.441. 2. There we go. Those are our 2 solutions. Okay? Okay. Oh, total of 4, though. If this had been all solutions instead of 0 to 2 pi, remember to just slap on that plus 2 pi into those problems. Yeah, okay. I sort of feel like we're there. I don't know. How about this one? One last one. Or one last set of last ones. X equals 1. Okay. 0 to 2 pi. And all solutions. Do them both. Come back. We'll check. Hey, so I'm dividing by 2. And then people take the square root. And they don't know what that is. But here's the thing. You do know what that is. It's the square root of 1 over the square root of 2. And if you rationalize, you get root 2 over 2. And don't forget, because you took the square root of both sides, you need that plus and minus. Plus and minus root 2 over 2. So when is sine plus and minus root 2 over 2 on 0 to 2 pi? Well, that happens at pi over 4, at 3 pi over 4, at 5 pi over 4, and at 7 pi over 4. And again, with all solutions, well, with all solutions, I could slap on a plus 2 pi into those. Oh, God, it's going to be so much writing. Do we really have to? Yes, Mr. Coop, because we don't want to think about it the other way. All right. But really, it's so much less writing to do it the other way. 5 pi over 4 plus 2 pi n. 7 pi over 4 plus 2 pi n. Oh my goodness! All of these solutions are pi over 2 apart. X equals pi over 4 plus pi over 2 n. And I can see that here. There's pi over 4. There's 3 pi over 4. There's 5 pi over 4. There's 7 pi over 4. When the amount of rotation is the same in between each of the solutions, you can just add that same amount, that pi over 2, to the first solution. Okay, but really, my excuse for doing this problem was not to solve that one, but instead to solve this one. Okay, so 0 to 2 pi and all solutions. And if you get the correct answers for both of these, I'll acknowledge that you are comfortable and ready to solve multiple angle problems. Okay, so yes, we get to a remarkably similar place that we did in the last one. And we take the square root, yup, 3x equals plus and minus root 3, sine 3x is plus and minus root 2 over 2. Okay, so that's going to be 4, 0 to 2 pi. 3x equals, I gotta go around 3 times, and there are 4 solutions each time. The positive brings 2, the negative brings 2. I'm going to have 12 solutions here. Yikes. So I get pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, 9 pi over 4, 11 pi over 4, 13 pi over 4, 15 pi over 4, 17 pi over 4, 2, 4, 6, 8, 19 pi over 4, 21 pi over 4, and 23 pi over 4. And then divide everywhere by 3 to turn these all into 6s. Okay. 6. Hi, dear. Hey, everyone. My wife has come to join us. Isn't that cool? So these are our 12 solutions. Now, what would the all solutions case look like? Wow, that's a thing you're wearing, isn't it? Can't quite see it. I think my wife is wearing her wedding gown in front of us, and that's really quite something. Yeah, all right, okay. By the way, if you don't remember what your partner's wedding gown or suit was,
you're in trouble.
See? Yeah. Life is filled with so many tests. It's an infinite number of tests. Those of you who say to me, Mr. Gupta, I have test anxiety. Oh my goodness, your life is filled with tests every second of every day. You didn't just run into Safeway and buy all the ice cream and then eat it all. You would have failed that test. That's not a good test. Okay, so back to us. I wanted all solutions for this. So I'm here and I say, okay, all solutions. But remember, with all solutions, I'm only going around once. So 3x equals pi over 4 plus 2 pi m and 3 pi over 4 plus 2 pi m and 5 pi over 4 plus 2 pi m and 7 pi over 4 plus 2 pi m. Ugh, I hate writing that. I would so much prefer to write 3x equals pi over 4 plus pi over 2m. Here, we now have to divide by 3. So many 3's. And so x equals pi over 12 plus 2 pi m over 3, and 3 pi over 12 plus 2 pi m over 3, and 5 pi over 12 plus 2 pi m over 3, and 7 pi over 12 plus 2 pi m over 3. Ta-da! Or, because you're lazy like me, x equals pi over 12 plus pi over 6m. So much less right. Okay, so multiple angles. You should be able to do 0 to 2 pi. You should be able to do all solutions. You should be able to solve trig functions with factoring. You should be able to use your calculator and recognize when to use your calculator on problems like this. Yeah, this was the unfactorable one. This is the one that does factor for one unit circle value, and one was calculator. I think that was 2/3. Don't forget the plus and minus when you take the square root of both sides. This is definitely a factor case. And oh God, don't subtract 2 from both sides. Yeah, but other than that, you should be pretty ready. And good luck with your assessment. Take care, everyone.